In order to do transformations on higher order polynomial functions, let's go back and review what we did with quadratics. The first equation, this was called vertex form of a quadratic equation because its parent function was y equals x squared. So if we have the equation y equals negative 3 x plus 5 squared minus 4, the transformations that are occurring are the negative being multiplied in front of the original function always reflects over the x-axis. The book sometimes calls it reflects in the x-axis instead of over. This just means it takes our parabola and instead of opening up, it opens down. It flips it over. The 3 in front, it vertically stretches. When the number being multiplied in front of the original function is greater than 1, we say that it stretches or it becomes narrower. And when the number being multiplied in front of the original function is between 0 and 1, we say that it vertically shrinks or compresses. It becomes wider. Inside the parentheses is what moves the graph left or right. Because the original definition had an x minus h. When it says x minus a number, that's a transformation to the right. So if it says x plus a number, that's a transformation to the left. It might say in the book a horizontal shift 5 units to the left. We were just saying 5 left. And then any numbers on the outside of the original function being added or subtracted move the graph up or down. If it's plus, it moves up. If it's minus, it moves down. So in this case, it moves down 4. Or the book might say it's a vertical transformation. I can't even spell right. Let's try that again. Transformation down 2. Even though we could obtain the graph of any quadratic function from the graph of the parent function, this is not necessarily true of all power functions. Power functions being functions that are raised to some power, like x cubed, x to the 4th, x to the 5th. There are transformations that can be made if the equations are written in a certain format. Notice that this is a cubic function because the x minus h is raised to the 3rd. Well, it can be transformed in the same way as long as it's in this format. So if I said y is equal to negative 2 x minus 1 cubed plus 3, I tell you that the parent function, y equals x cubed, which looks like this, could be moved 1 unit to the right, 3 units up. It would be reflected over the x-axis, and it would be stretched vertically, which means it would be narrower. So it would look something like this. I would move this is called the point of inflection. I don't believe our textbook called it that, but 0, 0 is the point where the graph of x cubed seems to flatten out a little bit. So I'm going to take that point and I'm going to move it. So it's going to go 1 to the right, 3 up, and then instead of going up from left to right, it's going to go down from left to right, and it's going to be narrower. So it's going to look something like this. So it gives us an image of what the graph kind of looks like. In order to do this translation in problem 1, we're going to do it in a very similar fashion to the way that we did it with quadratics. So in problem 1, it says, what is an equation of a graph of y equals x cubed under the following sequence of transformations? A vertical compression by a factor of 1/2, a reflection in the x-axis, a horizontal translation 5 units to the right, and a vertical translation 2 units up. So starting with the equation y equals x cubed, and the very first translation A vertical compression by a factor of 1/2. That's what occurs when you multiply the original function by some number. The next one says a reflection in the x-axis. A reflection in the x-axis is what occurs when you multiply the original function by a negative. A horizontal translation 5 units to the right. Horizontal translations take place in a set of parentheses. If it's to the right, it's going to be x minus 5. If it were to the left, it would be x plus 5. And then the last one is a vertical translation 2 units up. Up and down gets either added or subtracted at the back end of the original function, and up is 2. So this would be the translation of x cubed that's been reflected over the x-axis. It has a vertical compression of 1/2. It moved 5 units to the right and 2 units up. Because we're talking about transformations on cubic functions that are very similar to the ones on quadratic functions, the zeros of a cubic function in this format that looks like vertex form, there's only going to be one, and I'm going to show you why. If a, h, and k are real numbers and a does not equal 0, how many distinct real zeros does y equals negative a, x minus h to the third plus k have? So let's think about this problem algebraically. How would I solve for x? Because that's the zeros, right? It's when x is equal, or when y is equal to 0, we want to know what x is. So in order to solve this, the first thing I would do is I would subtract k. And then I would divide both sides by negative a. The nice thing is 2 negatives are going to make a positive, so I'm going to have k over a is equal to x minus h cubed. When we get rid of a square on something, the inverse operation is square rooting. To get rid of a cube on something, the inverse operation is cube rooting. So we would cube root k over a. And now the last thing that would happen is we would add h to the other side. And this is what x would equal. Well, x is going to be one number, disregarding any multiplicities. Just to repeat, not all higher order polynomials can be found by doing transformations. So this particular cubic function, y equals x cubed minus 2x squared minus 5x plus 6, if you graph it on your calculator, you'll notice that it has 3 zeros, and the 3 zeros are at negative 2, 1, and 3. This graph is not in that vertex form looking shape, so you can't just find the transformations on it. This is the same for quartic functions as well. In problem 3, we want to find a quartic function that only has 2 real zeros, one at x equals 5 and one at x equals 9. So here's the thing. A quartic function is a 4th degree polynomial. If it only has 2 real zeros, that means the other 2 zeros are imaginary. There are 2 ways that we can go about doing this problem, and you're probably going to like this first method, actually the second method, better than the first method, but I present them both to you anyway. The first method is going to be using transformations. So, transformations mean, what's the parent function? Well, the parent function of a quartic function would be y equals x to the 4th. If you graph that on your calculator, you're going to see something that looks like this. It kind of looks quadratic, but it's a little flatter near the vertex. So now if I want my zeros to be at 2 and 5, the shape of the graph, this is how I'm going to start. I'm going to start by making a 0 at here and a 0 here. I'm sorry, I didn't say 2 and 5. I meant 5 and 9. I want you to notice that the difference between 5 and 9 is 4. That means that it is 4 spaces from one 0 to the other. Well, if I do that, then what's going to happen is I'm going to have to, well, let me redo this a little. I'm going to have to shift my graph down in order for this parabola-looking shape to hit the x-axis at 2 and negative 2. So since there are 4 units between them, and my zeros right now are at 2 and negative 2. The reason they're at 2 and negative 2 is because all I did was I took my graph and I knew that there had to be 4 spaces between the zeros. So in order to make that happen, you have to take the graph and move it down. And then it will hit the x-axis at these 2 locations. The basic translation, you're going to take that 4 and you're going to square it. So y is going to be x to the 4th, and then it's going to be minus 16. And the reason that it's minus 16 is because we translated the graph down. Okay, now we have to do another translation because we don't really want the zeros to be at 2 and negative 2. We actually want them to be at 5 and 9. It looks like I didn't give myself enough space. 3, 4, 5, 6, 7, 8, 9. So now I'm going to have to move my graph to the right. Well, how many spaces to the right am I going to have to move it in order for it to hit at 5 and 9? Well, I need this one to get to 5 so that the other 0 is at 9. So how many spaces do I move it? I move it 7 to the right. Well, how do you write 7 to the right? You write it like this. So this is a graph that would have 2 real zeros at 5 and 9, and the other 2 zeros would be imaginary because it's a quartic function. Let's do another method that you might like better. We'll call it method 2. All right, so I want my zeros to be at 5 and 9, and it's a quartic function. So one of the things I can do is I can do that backwards method where, well, one of my factors is x minus 5, and one of my factors is x minus 9. So the other 2 factors have to give me imaginary numbers. Now, reminder, imaginary roots come in pairs. You cannot have one imaginary root. Not only do they come in pairs, but they are complex conjugates of one another. That means that one of the roots has to be a plus bi, and the other one must be a minus bi. So one of the things I could do, I'll call it times q of x. So I need another factor over here that's square in some fashion. So I can pick anything that's going to give me imaginary roots. So here's an example. X squared plus 4 will give me imaginary roots, because if you set it equal to 0 and you solve, you will get plus or minus 2i. Or you could use x squared plus 9, because it will give you the imaginary roots plus or minus 3i. Or you can use x squared plus 1. Do you see where I'm going with this? Whatever this square factor is, it's going to be x squared plus a number. And it doesn't even matter what number. You could give a number that's not going to be an integer when you take the square root. It could give you radicals. You can use x squared plus 5 or x squared plus 7. Whatever you use, it's going to be x squared plus something in order to get those imaginary roots. And like I said, there's no one right answer, like which one of these do you have to pick. It doesn't matter which one you pick. So because this is the one the book uses, I'm going to use this one. So now I'm going to go and I'm going to erase this. So we're going to use, I've got x minus 5, I've got x minus 9, and then I'm going to use x squared plus 1. So now this is a fourth degree polynomial. Remember, you can tell the degree of a polynomial by adding up the x's. 1, 2, 4. Okay, so now we're going to multiply this out to find out what the quartic function is. I'm going to multiply these two together, and I'm going to do the shortcut. It's going to be x squared. The middle coefficient is going to be the sum of these two numbers, which is negative 14. And the last number is going to be the product of those two numbers, which is 45. Now, to finish off my multiplication, I'm going to use the box method because I'm less likely to make a mistake. So I've got x squared, negative 14x, and 45. And then I've got x squared and 1. So x to the fourth, x squared. Negative 14x to the third, negative 14x. 45x squared and 45. Notice that my like terms are not necessarily on the diagonal, so be careful. The first term is x to the fourth. There's only one x to the third, so I've used that. I have to add those two together, so that's going to give me 46x squared. And then there's only one x term, and then one constant. And this would be a sample quartic function that has only two real zeros at 5 and 9. I mentioned this already. I'm going to mention it again. We can only do basic transformations on higher order polynomials if they are in this vertex form, just like with quadratics. So a fourth degree polynomial in this form can be moved using basic transformations. No other quartic function, like the one in the previous example, could be done that way. These are all called power functions. They all fall under this family. And power functions arise in many real-world contexts related to the concept of direct variation. So a power function like y equals a times x to the b, we say that y varies directly with x to the b power. We have done direct variation before, so this is a good time to review it because we haven't seen it in a while. So let's do a direct variation problem. Wind farms are a source of renewable energy found around the world. The power P in kilowatts generated by a wind turbine varies directly as the cube of the wind speed V in meters per second. The power output of one turbine is 600 kilowatts at a wind speed of 8 meters per second. To the nearest kilowatt, how much power does the turbine generate in a 10 meter per second wind? So a review, y equals kx was direct variation. The nice thing about direct variation is it could be solved using a proportion. Call it x1 over y1 is equal to x2 over y2. The only thing is, this problem's a little bit different because it tells us that the power P is generated by the wind turbine and it varies directly as the cube of the wind speed V. So the power P is equal to some constant, and the book calls it A, so I'm using A here, but you could use K as well, times the velocity V cubed. If you want to use the equation to solve it, that's what the book does. I'll show you that method, but I will also show you how to use the proportion. So, in order to use the equation, since I know that the power is 600 kilowatts, when the velocity is 8, I could solve this equation for A, and then I would have an equation that I can plug 10 back into to find the power. So, I get 600 is equal to 8 cubed is 512, and then I divide by 512, and I get approximately 1.1719. That means the equation that represents this situation is P equals 1.1719 V cubed. Now I can plug 10 in for V to find out what the power is for that wind turbine. So 1.1719 times 10 to the third is going to be 1,171.9 kilowatts. Well, what if you wanted to use the proportion? Now, remember y is your output and x is your input. So V1 cubed over P1 would equal V2 cubed over P2. How did I come up with that proportion from this? Well, remember that we said that the power varies directly as the cube of the velocity. So notice that the cube of the velocity ended up in the proportion. So what I could have done was I could have done 8 cubed over 600 is equal to 10 cubed over P2. And then I could have just solved that proportion, cross multiply. I would have gotten 512 P2 is equal to 6. Let's see, 1, 2, 3, 4, 5. And when I divided, I would have gotten 1,171.9. Both methods are acceptable. You can use whichever one makes you happy.